Okay, concavity intervals, points of inflection. So, as you know by now, this is all about the second derivative. Where is it positive? Where is it negative? Where is it zero? So, let's get a second derivative. Our first derivative, the derivative of x is 1. Now, if you haven't done trig derivatives yet, you need to know that the derivative of cosine x is negative sine x dx. So negative sine of whatever times the derivative of whatever. In this case, the whatever is just an x, so that's not going to be a big deal. So the derivative of x, we get 1, and then we get minus, and the derivative of cosine x is negative sine x. And there isn't any chain rule to happen here because the thing inside the argument was no more complex than just an x. So when the dust settles on this, we have our first derivative is just 1 plus sine x. And now our second derivative gets simpler yet. The derivative of 1 is 0, so goodbye. And the derivative of sine x, as you may know already, is cosine x dx. So here we get just cosine x. Why didn't I say dx? Because it's already been divided over. When we write this notation, it's understood that we've done two derivatives of y, and we've divided by dx twice. Once when we did the first derivative, once when we did the second one. So, that's nice. Our second derivative is just cosine x. And if we want to find critical values for this, or interesting values for the second derivative, we want to know where is it undefined. The answer is never. Cosine is defined everywhere. And we want to know where is it 0? Well, cosine is 0 a whole bunch of places, including pi by 2, or 90 degrees, 3 pi by 2, or 270 degrees, 5 pi by 2, 7 pi by 2, and so forth. But these are the only ones that interest us because we're supposed to stay on this interval 0 to 2 pi. So, pi by 2 and 3 pi by 2 are the only places where the second derivative might do something neat. Let's see if it does. Pi by 2, we have 3 pi by 2. This table won't be all that big because the second derivative is only one piece. It's just cosine x. We don't have to worry about a bunch of different factors and combining them together. So, if our angle is less than 90 degrees, let's say it's 45 or something, then its cosine is positive. We're in quadrant 1. Cosine pi by 2 is cosine 90. That's 0. Between here, we're between 90 and 270, meaning we're in one of the left two quadrants, quadrant 2 or 3, so cosine is negative there. 3 pi by 2 is 270. Cosine is 0 there. And once you go past that, you're over into quadrant 4 where cosine is positive. So that means our function is concave up. Here in the middle, it's concave down, and then it flips back to concave up. These places in between where the concavity changes are what we call inflections. And so we have an inflection at pi by 2. And we have an inflection at 3 pi by 2. Those are places where the concavity changes between either from up to down or down to up. And if we're going to give the locations of those points, these are the x-coordinates. We can go back to our original function to find what the y-coordinates are. So for this first one we get, I'm going to do this off to the side, it's x minus cosine x, so we get pi by 2 minus the cosine of pi by 2, which is pi by 2 minus cosine pi by 2 is actually 0. Yeah, so our y-coordinate is just pi by 2. And I guess that'll happen again for this other one. Our y-coordinate is going to be x minus the cosine of x. But again, cosine 3 pi by 2 is cosine 270 degrees, so it's 0. So our y-coordinate comes out to be just 3 pi by 2. So our intervals of concavity would be that we're concave up from 0 to pi by 2, and also from 3 pi by 2 to 2 pi. We're concave down between pi by 2 and 3 pi by 2, and we have inflections in these two places.